And I'm going to take us to the PowerPoint. Okay, so you should be able to see the PowerPoint. Is that true?
Yes.
Okay. Please let me know if you lose the picture, and I'll try to make my error go away. So here we go. All right, Chapter 8, we're talking about sampling, variability, and sampling distributions, right? So when you think about the word sampling, that is sort of a process, and it probably is an ongoing process. You're always thinking about the sample that is very, very important that you're going to get some information from. Okay, so we really want a sample that is representative of the population. And I like this big picture look at it. So the big picture is that the population here, okay, is really what we're interested in. We're really interested in the population. Now, because we can't measure everybody in the population, we have to get an estimation of what we want to know through a sample. So this sampling process is very, very important. This idea of getting a sample that is representative of the population, all right? So I also started to tell you about, or have taught you, we have measurements of the population, and we call those measurements parameters. Okay, parameters of the population. And the sample gives us a statistic. So the population has parameters, the sample has statistics. So we're using statistics from the sample to give us an estimate of what we really want to know about the population, and that's the parameter. And that's really what statistical inference is all about, taking a statistic and inferring something about what we want to know in the population. Okay, so we've been using descriptive statistics almost all the time, excuse me. Okay, so here we have a example. Okay, we're talking about the parameter mu. Mu is a population mean. Okay, a population mean. So we're trying to get what we know is a true population mean here. All right, so we're looking at the fat content of the quarter-pound burger, okay? And so we want to know something about that fat content. All right, so we know that there's a true like value that goes along with the variable, okay? But we don't know all about the population. So we're going to use a sample. And in this case, we're going to use 50 hamburgers, and we're going to determine the fat content of each one of them. All right, so would the sample mean be a good estimate of mu? Now, if you wanted to know, the sample mean is a statistic. It is X bar. So the sample mean, X bar, is that a good estimate of the population mean, U. How close is the sample mean to mu? How close is X bar to mu? Will other samples of a sample size of 50, will they have the same sample mean? So these are the types of questions that we're asking about sampling. And we're interested in these things, and we're going to look into it a little bit more. So these types of questions go along with a sampling distribution. And so this is using sample statistics to build a sampling distribution. Now, when I say sample statistic, that could be X bar, it could be the sample standard deviation, which is S, it could be P hat, which is a proportion. All those are statistics. Okay, so recall that the sample mean in this particular case is a statistic. All right. So a statistic is a number that is computed from the sample data. We use the average of the sample or the sample mean just because it's easy to work with. All right, some of the other statistics that we might want to show are these as an example. So X bar is the sample mean, S is the sample standard deviation, and we could have P hat as the sample proportion. And so we'll go through these through this lecture. All right, so the observed value of a statistic depends on the sample, okay? And the sample that is selected. And we should expect that there is variation between samples, okay? So if we had two different samples from the same population, those samples probably will be different. Okay, and let me get into that a little bit more. So there is sampling variability. The sample, two samples will have different sample means. Okay, so this is an example of a population, okay? So Wolf City College has a fish pond, and there are 20 fish in that pond. I don't know how they measured that or detected it, and I'm not sure how they got the lengths of the fish either. But here are the 20 values in that population. All right. If we were to randomly catch a sample of 3 of the fish in the pond and measure their length, what would be the mean length of the sample? All right, let's take a look. Well, we're going to go ahead and do the first sample. This is the first sample, and the data are 6.3, 2.2, and 13.3 inches. So the sample mean, X bar, the sample mean of these 3 values is going to be 7.27 inches. All right.
So would the values in green be the population, and then the 6.3, 2.2, and 13.3 be the sample?
That's exactly right, okay? We don't usually think of a population of this size. This
Mhm.
is kind of small for a population, right? But
Yeah.
if it was defined to be that, okay, that is what the fish pond is, we could call it a population. All right, good question.
Mhm.
Okay, so how about if we took another sample? Okay, we threw we put these uh, fish back into the pond and we get another sample. Okay, another sample that goes along with the population of 20 fish. All right, so here is another set of 3. And this is 8.5, 4.6, 5.6 inches. And the sample mean is 6.23. Now, let's stop here and start to think about this. Number one, we took a random sample of 3 from our pond, from our 20 fish. Okay, and we got one sample mean. Then we threw the fish back in and took another sample. Same thing, only this here is the sample mean, 6.2 versus 7.3. So the two sample means are not the same. Okay, and if we got a third sample, all right, so we got another set of 3 values, and the sample mean is 10.87 inches. So there's quite a bit of variation that goes along with this problem. So we have 3 different versions of the sample mean coming from the same population. Okay. So if the true mean was 8, okay, and that could be, and so these values right here, the 3 X bar values are around the mu of 8. Some are close and some are very far away. So this is an example of sampling variability, the variability between the sample means. Okay, so if we were to get all of the possible samples of a sample size 3 in the population, that would be a combination of all these values, and we would have 1,140 sample means if we had all of the combinations of sample size of 3. Okay, so this here all is actually this population right here. We're now talking about the sample means, right? So a sampling distribution is a distribution that has all the possible sample means with a size of 3. This would be a sampling distribution of the mean. Questions about this? This is kind of a concept that you have to think about. Okay, so let me go to this here. Can you see this applet? Hello?
No, we just see the word applet.
Okay, let me go get it. Sorry, hold on. Okay, do you see it now?
Yeah, we can see
Yeah.
it.
Okay, very good. All right. So this is a simple thing, okay? It's sort of a random number generator, okay? And we're going to try to set this up so I can get you to think about the sample means, okay? So for example, this here, this applet is a population of 144, okay? So that's the size of the population, okay? And we can select any type of sample size we want, okay? Here is the default, and it's 10, okay? The sample size is 10, so we're going to take 10 values out of the 144 and sample. And so what you can do is do this sampling, all right? And you can reset it and do it again, and you'll see that the values are quite different, and that shouldn't be any surprise. We can copy that sample, okay, and put it into a spreadsheet, for example, okay? And I'll show you that in just a second. We can change, okay, we can change the sample size to something like 20, okay? And again, sample, and you'll get 20 values, and that's your sample. And of course, we can reset it, do it again, and then we can start to clip these and put them into a worksheet, okay? All right, so let me, any questions about this while I have it up? Okay. So let me go back, please. Sorry, guys. Oh my. Okay. You can't see that either. Sorry. Okay. Sorry about that. Okay, so back to the applet. Here is the a worksheet, okay? And here is the population. This column right here is the population, and the population goes all the way down to 144, and we have 1 sample, 2 samples, 3, 4, 5 samples, okay, of values coming from that population, and the sample size is 10, okay? The sample size is 10. And each one of these, the sample size stays the same, all right? And what I want to show you here, okay, is the variability that goes along with these values. Okay, so there's quite a bit of variation right in through here. All right, now we could change the approach, and we can use samples that are the sample size of 20, and that's here. 1, 2, 3, 4, 5 samples. So the samples here also give you averages of the sample that are variable. Okay, is everybody following me?
Mm-hmm.
So if we did this many, many, many times, we could take these values right here, and look at their distribution, all right? And I'm going to say one more thing about this before I get out of it. This here, a sample size of 10, is going to have greater variability than the ones down here with 20, all right? This is going to have greater variability than these numbers right here. Does everybody sort of see that?
Yeah.
Okay, that's important. Okay. So here we have another idea here. Okay. So let's just think. Okay. I'm going to try to get you back to the fish pond. Okay, say that we have only 5 fish in the pond. Okay, and we want to know what all the possibilities, all the possible sample means. Okay, so what is the mean and the standard deviation of this population? Okay, that's the population. Okay, we're taking this as a population, and we're saying that this number here is the mean of this population, and here is the standard deviation of these numbers here. All right, so that is the case. So if we took a sample of a size 2, each one of these, we could actually get all the possible combinations, because the combinations are about 10, okay? All right, so here are the combinations of this here, and all the combinations are 2. Each one is 2, okay, sorry. So what we do now is we take the sample mean. That is, we would take the average of these two numbers, and that number would be 9.15. The next set of two numbers would be 7.75. And we would take all these 10 sample means and start thinking about what they are telling us. All right? So these are the values that go along with a sampling distribution for samples of a size 2. I'm emphasizing this, the sample size. Okay, and what would the mean and the standard deviation be of the sample means? What would be the mean of the sample means? Okay. The mean of these sample means is the same as the population mean. Okay, everybody sort of see that? Questions? Okay, here is the standard deviation of these values right here, right? The standard deviation here is the standard deviation of these numbers right up here. Okay, so the standard deviation is different here than here. But when we look at the population mean and we take the sampling distribution, we get the same number. Okay, how do these values compare? The mean is the same and the standard deviation is different. Okay, now we're going to change the sample size to 3. Okay, the sample size to 3, and we're going to go through the same idea. How many samples of a size 3? All right, so here is the 3 triplets here, okay, all the way down. Okay, and so here is the mean when we use a sample size of 3. What is going to be the mean of these X bar values? What is going to be the mean of these values?
Will it be the population mean again, the 7.84?
That's exactly right. It's going to be the population mean. So we can determine the population mean by taking these samples, okay? So we have to have all the combinations to do that, but we can show that the sum of the means of the sample means equals the population mean. Okay, so let me go one step further, and I'm going to ask you to think about the standard deviation of the sample means. Okay, I'm looking at this number right here, these values right here, and the standard deviation of these values right here is 1.33. All right, now let me go back one step, one slide. This number right here is 1.9. Let's make it 2. Let's round it off and make this standard deviation with a sample size of 2. Okay, a sample size of 2 is 1.998. And I want you to compare that to 1.33. So what has happened to the standard deviation when we increase the sample size?
It decreases.
Say again?
The standard deviation decreases.
That's right. Okay. Is everybody following that? All right. Okay, so here's sort of a summary. Okay, the mean of the sampling distribution equals the mean of the population. Okay. As the sample size increases, the standard deviation of the sampling distribution decreases. And what that means is as the sample size gets larger and larger and larger, the variability across the sample distributions are going to be getting now more narrow, more narrow, more narrow. All right, so as the sample size goes up, the standard deviation of the sample means goes down. Excuse me. All right, that's rule number one. This is rule number two. Okay, so here is what is called the standard deviation of the sample means. This term here is called the standard error, okay? Standard error. We're taking the population standard deviation and dividing it by the square root of the sample size. Okay. So there is an assumption here with certain things like if the population was infinite, which no population really is infinite, it would be a rule here. But if the population is finite, we have to be careful about how we use that population. We can't sample, the sample size can't be any more than 10% of the population, okay? The sample size cannot be any more than the 10% of the population, all right? Questions? Okay. Okay, so we did not uphold the assumption in our prelude to this this issue, this concept. Okay, so here we go. Here's a question out of a science journal. All right, the distribution of platelet volumes in patients who do not have metabolic syndrome is approximately a mean of 8.25, standard deviation of 0.75. All right, and so this gives you a sense of what the standard deviation, what the normal distribution should look like, okay? So it approximates normal distribution, and this bell-shaped curve is a normally distributed distribution, okay? So we have the mu is 8.25, the standard deviation is 0.75. Okay, so let's think about this. If we were to generate 500 random samples of a sample size of 5 and compute the sample mean for each. Okay, and that's what I was showing you with the applet. I was trying to show you how you could do this. Now, Minitab does it very easily, as does other platforms make it very easy to generate 500 random samples. Okay, so let's think about the same thing. We're taking we're taking 500 random samples. One is going to be 10, a sample size of 10. Second one is going to be the sample size of 20. Third is 30. Okay, so we're going to see the histograms and show those for each one of the sample size. Okay, so let me just go back and sort of show again. So we're going to use different sample sizes with the same number of random samples. Okay, so we have histograms with a sample size of 5, 10, 20, and 30. Okay, now what is the center of this particular histogram? What is the value of this?
8.2.
8.2. Okay. Is that Logan? That's
Yeah.
okay. And you remember that from a slide or two ago? Right.
Yeah, and it like the scale of the.
And the scale. Okay. Do you see as the center of 8.2 for each one of these?
Yeah, I would say
Okay.
that they're all around 8.2.
Okay, so the 500 random samples that are making up each one of these histograms gives us the same center, and that center is consistent with the population mean. Okay, everybody got that?
Mhm.
Okay, so what do you see going from 5, a sample size of 5, 10, 20, 30, what else is going on?
The standard deviation gets smaller, so there's less variability.
Okay, Katie, is that you?
Yes.
Okay, Katie, so what you're saying is that the values that are across the x-axis is getting more and more narrow, more closer to the center.
Yes.
Okay. All right. So as the sample size goes up, the spread of the histogram is narrowing. Katie, while I have you here, would you see a bell-shaped curve in each one of these?
Yes.
Okay, so 3 things to walk away from here. Number 1, okay, when we start to think about a sampling distribution, and that's what these are, all these are different sampling distributions. If we have a sampling distribution, the center will be around the population mean. That's number 1. Okay, and number 2, the population standard deviation will fall as the sample size increases. That's number 2. And yes, every one of these density curves will be bell-shaped. That's number 3. Okay, and that's what we're sort of starting to think about. All right, so I'll leave you with this. Rule number 3, when the population distribution is normal, the sampling distribution of X bars or the sample means will also be normal too. Okay, and with that, I'll stop and take any questions.
Does that just mean that it will be like always be a bell-shaped curve?
Okay, I think I'm I'm talking with Logan. Yes, okay. If the population distribution is normal, and we may or may not know that, okay, but if we do know that, we will see that all of these sampling distributions, no matter what the sample size is, okay, is going to be bell-shaped too.
Okay.
Did that make sense?
Yeah.
Okay, thank you. Other questions? Okay. So I think we got some hard thinking to accomplish, okay? And I'm going to draw up a homework assignment, and I'll give that to you on Friday. Okay, we got this Chapter 8 down. Take a look at the first couple pages of Chapter 3 for Friday, and then we'll continue along these lines. Other questions, comments? Well, it's great to have you all back.
Thank you.
Thank
Have a
you.
great
Thank
day.
you.
Have a great day.
Thank you.